Today we're going to start a new series, Narnia. This series mainly covers things like buffer overflow, binary exploitation, and so on. Okay, so let's get started. This is the server we need to connect to, and this is the port. Okay, and this is the username and password. So once we have this information, we can just log in, and you can see that data for these levels can be found in Narnia. Okay, so /Narnia. So let's go. SSH Narnia 0 at narnialabs.org and -p. So this is the username, and Narnia 0 is also the password. Now we're here. Let's move to /Narnia. Okay, so here we can see a bunch of files, right? So for Narnia 0, you can see that there is Narnia 0 and Narnia 0.c. So if you just see the permissions, you don't have permissions to open other files. Okay, as Narnia 0, you can only open these two files. Okay, so this will be our point of interest. You can also see that this particular file is owned by Narnia 1. Since it has setuid permissions, Narnia 0 can also execute this file. Let's clear that. Let's open Narnia 0 and let's see what it has. Okay, correct val's value from 0x41414141 to 0x dead beef. What they're trying to say is there is a variable called val, so you need to correct this val's value. Okay, so we don't know how to do that, right? We don't know the code, so we just typed some random value and then we'll see the output. If you see ASCII table, this 41414141 is nothing but A. Okay, so hex value of A. Let me show you that. ASCII table.com. You can see that 0x41 is nothing but capital A. We know that this is A. Okay, so we need to change this part to this. Let me type some characters to show you what it actually does. Okay, let me type bunch of B's. Let's see what happens. As you can see, it has changed it from 41 to 42, which means this capital B refers to 42, right? So what we have essentially done is we have changed this val's value from 41414141 to 42424242. We don't know how much length this is, right? But they have given a file called narnia.c. Let's see that file, 0.c. So this is the file you got. So these are the standard headers, standard C headers / include something something. This is the main code. So here they have said this is long integer which has the value of this, and then they have said that this is some kind of character and this name of it, and it contains 20 characters. And we have also seen these two values right on the screen right here. Okay, so basically they are just simple printf, and then we need to enter some value here. So scanf is asking for 24 bytes of data. So S is refers to string, so 24 bytes of data. Once we have inputted the data, then it shows the buff value and the val's value, and then it is going to check this val's value to dead beef. Then it is going to take the user permissions. It's going to get this UID and then set this UID, and then what is it going to set to? It's going to set to this shell. Okay, once this shell is there, then it is going to end right here. So this else statement will not execute, and then it's going to return 0, and then it's going to exit. If it is not equals to dead beef, then it's going to print way off and then exit with exit code 1. How to imagine this part? So you need to understand at memory level what's going on. Okay, so whenever we start assigning some values to variables or some functions, all these things come in the stack format. Okay, so to imagine that, these two images would help. So this is how the program usually runs. Okay, it remembers the arguments. If we have any arguments, this one we don't have any arguments. It's going to keep adding all the important things, and then once we start executing the program, we know that once we reach to the val's value, we are actually setting it to 0x41414141. Okay, so we already know that, right? But what about this one? We are giving a space of 20 characters so that later you can enter something into it, right? Since we give the buffer of 20 characters, we can enter 20 characters or 20 bytes of data into this array. Okay, so this is how it actually stores the memory. It starts from highest memory and then keep allocating data as it starts adding arguments or variables or functions in this stack format. Okay, so this is the memory stack which actually happens. So in this image you can actually understand what's really going on. So we know that long val is actually given as long integer. It can accommodate 8 bytes, but we have only given 4 bytes of data into this, but it can still allocate 8 bytes of data. So what about this one? We have given 20 bytes of data to this buff variable so that it can allocate 20 bytes of data. You can count. So 1 2 3 4, 1 2 3 4 5, 5 4 is 20. So when we are accepting data into the buff variable, we are not accepting 20 bytes only, we are accepting 24 bytes of data. So it can start allocating data from the top, and once it reaches 20 bytes, it can still allocate 4 more bytes. And where does this bytes go? This 4 bytes of data will go into the next long val variable. So we'll see that in action. So now I will show you how to understand what's happening at memory level. Okay, so for that we can use GDB. So it is a debugger of a binary code. So we'll just say that Narnia 0 to be opened with the debugger. So it is going to ask you enable debug. Okay, so just accept it, and then now you are in debug mode. Okay, so you want this binary program to be converted into assembly language so that you can understand the code. For that you can say that disassemble main. Okay, so as you can see, this is a dump of assembler code for the function main. Okay, so the program starts from main function, right? So everybody knows this. So these are the values from which the memory distance of this particular instruction from main. Okay, so when you want to analyze this particular value, you say main plus 7. So our point of interest is at the scanf because we are entering this data. So this is user controllable data, right? We'll assign some breakpoint at this area. Okay, so how do we assign it? We'll say break and asterisk. So this is the pointer you're trying to say. So where is it? It is at main plus 54. So if you see this value, so this value should be equal to this value. Okay, so 91FC, you can see that 91FC is here. So basically we have assigned a breakpoint right here. So what does breakpoint do? So breakpoint just halts the program at this particular location. So let's enter some values. So to enter these values, so you have to run the program, right? So you say run, or you can simply add R, so which also says that it can run. Okay, so initially I'll just run this. Here's your chance. So we need to enter some data. Let's enter some data and see what happens. And as you can see, it is just halted at this breakpoint. Okay, so what is this breakpoint? So this is a stack pointer. So you can say that show 20 words of memory from stack pointer. So to understand this thing, I'll just tell you what it is. So X is to examine. Okay, so you need to examine some data in the memory. Okay, so how much memory you want to examine? You want to examine 20 words of memory. Okay, so we'll see the words of memory. What does words of memory actually mean? Okay, and then this X says that it should be shown in hex format. If you hit enter, you can see that this is the data that is being dumped. So here you can see that 1 2 3 4 and 1 2 3 4 5. So 20 words of data. Okay, 5 4 is 20. So 20 words of data from the stack pointer. So we know that we have entered some data, right? That data is BBBB, right? So we need to see this BBBB in memory. So what is this capital B refers to in ASCII table? It is 42, right? So you can see that is 0x42, 42, 42, 42 right here. And then you can see some null data, which is an empty memory that is allocated to this buffer variable. So how much is it? So if this is 4 bytes, 1 2 3 4, which is this one. So 1 2 3 4 and 5. So 5 4's 20 again. So 20 bytes of data is allocated to the buffer value. We know that val's value is 41414141, right? So what happens if I keep ABCD instead of this value? Okay, let's see that again. Okay, we'll just say run, and then we need to say yes because it will start from the beginning. So this is my chance, so I'll just say ABCD. Okay, so and again I can say the same thing. So here you can see that this ABCD is given in reverse order. Okay, 41 42 43 44, which means it is following little endian format. Okay, so if you can just check little endian, so this is the format it is actually following. Okay, so big endian format will go from left to right, but little endian format will go from right to left. To do that, we can say we have to give DCBA, and then you can actually see that it will come in straight order. Okay, so 41 42 43 44. So conclusion, so if you want to write something in memory, we should write in reverse order. Okay, so now question, so can we write the same thing directly to the memory? Let's try that. Let's try to write the hex values right now. Okay, so to enter hex values, you have to say \x, which means you are saying that you want to input hex values. Okay, so here you can say 42 and then just copy it just 4 times. Control C, Control V. So now you have given 4 bytes of hex values. So let's see what happens. So as you can see, it was not possible. So each character is detected as a byte. Okay, so you cannot input hex values directly like this. So what you have to do is you have to pre-process this hex value and then send it directly to the memory. So you cannot do it right here. So for pre-processing, you have to use pipe symbol so that you do the pre-processing first and then directly send it to the memory. Okay, we'll see how we can do that. So next you can see that since each character is detected as a byte, so we can see that there is 16 bytes of data that is being filled over here. Since the scanf can take 24 bytes of data, so can we overwrite this value with 42424242, which means B. So let's see that. So let's see if we can do and overwrite this value. Okay, so let's say run and then run from the beginning, and let's say B, and just copy this and just type 5 times. 1 2 3 4 5. Okay, so 5 is nothing but 20, so you have to say one more. Let's see. So as you can see, you were able to overwrite this value. Once you have overwritten this value, you can just continue the program. Okay, you can say continue, or you can just type C for continue. Okay, here you can see that val's value is been overwritten. Let's go back to the original program and exit this debugger, so we know how to do that, how to overwrite this. So all we can do is do some pre-processing and convert these hex values and send them directly to the memory. Okay, so to do that, you can say echo -e, so which will actually pre-process it, or you can give some shell function which is printf, and you can still do the same thing. Okay, so let's try with printf. Here what you need to do is you need to enter some data. So you already have this B, right? 1 2 3 4 5, and then just type it. Okay, let's see Narnia, and let's see what happens. Okay, this output is sent as input to the scanf right here. Okay, so it has detected something like this. So let's add 4 more B's, and you can see that it is completely overwritten. So we'll just remove the last 4 characters, and here, since this printf is a part of a shell function, so you can say that I can pre-process right here. Okay, by giving hex characters. So we know what characters to be given, right? Here let's try to give the same thing. Okay, So pre-process this one and say 4 bytes of B. Okay, let's see what happens. So we were able to pre-process this value and send it directly to the val's value. Okay, so we'll just remove this because we need dead beef. So we'll just remove this value and say that, so we need to give dead beef in reverse order. You remember, right? Little endian, DEAD, BE and EF. Okay, it will pre-process the whole thing and then send it to the scanf of Narnia 0. Okay, as you can see, we were successfully able to change it to dead beef, but we did not get the shell. Okay, so let's see why that is right here. So this function is able to get effective user ID and it is also executing shell, but it is just simply closing with return 0. Okay, it's not stopping right here. So we need to keep that input stream open. Okay, so there is a small trick you can use to not close the input stream. You can keep this whole thing in the brackets. Okay, to keep the input stream open, you need to end this command, and you can also keep cat, because cat can keep the input stream open. Okay, so I'm just going to copy this and just going to show you how cat can keep that input stream open. So if you simply type cat, so you can see that it is just blinking right here, right? So it's just waiting for us to input something. So the input stream is open in this case, right? So if we enter some data, it will give that as an input to the cat command. And this cat command, where is this cat command going? So it will go to the shell. So this particular command will say that, so this is a printf, and this will give this much data and pre-process it and send it as an input to the Narnia, but also keep the input stream open. Let's see what happens. As you can see, it is blinking right here. So this dead beef has opened a shell right here, and this cat command is keeping that input stream open. So which means we have essentially have this shell open right now with the effective user ID of Narnia 1. So to confirm that, I can say who am I, which is Narnia 1. Okay, actually currently you have a shell, but you can get the password anyway. But what I want to show you is, do you have to keep all B's? No, you don't have to keep all B's. You can essentially remove all this and keep some random characters of 20 bytes and followed by this dead beef, and still it would work. So who am I? Narnia 1. So understand this underlying logic, because this would help you solve this really easily. Okay, so now you know that the password is /etc/Narnia_pass and Narnia 1. So this should give us the password. Okay, so I hope you have understood this. And there is one more thing I want to tell you. Okay, so is the code secure? The code which is given right here, is this code secure? Is this the correct way of writing the code, right? So turns out that this code, the way that it is written is secure, but deliberately they have made this into 24 bytes. Okay, check this out. So when using scanf to read strings, it is important to limit the string length to prevent the buffer overflow. Okay, so this particular code can actually prevent buffer overflow, this particular string, because we have limited it to 24 bytes. Okay, so let me tell you one more thing. So let's use the GDB to execute Narnia 0 and disassemble main breakpoint at main plus 54. So we know that this is the particular location, right? So now let's run it. So let's give lots of B's this time. Okay, so this is definitely more than 24 bytes. Will it even bypass this 24 bytes and go beyond 24 bytes? We know that it goes till 24 bytes, but does it go beyond 24 bytes? Let's check this out. Stack pointer. So here you can see that it can go till here only. It will never go beyond 24 bytes of data. So from this, you can say that, so the way it is written is secure, but they deliberately changed this buffer to 24 bytes so that you can get something out of here. If it was 20 bytes instead of 24 bytes, it would never overflow this buffer and reach this buffer. Okay, it will never do that. Okay, so I hope you get it, and I'll see you guys in the next one. Peace.